So last time, what we did, we talked about the basics of the resistors and Ohm's law and the basic concepts of node and mesh and things of that sort, the branches. And we saw that it was an abstraction. Over the last couple of lectures, what we've seen is that we start from a physical thing and then we turn it into an abstraction. Really, if you think about the chain of abstraction, there's several abstractions happening at different levels in that process. What you start with is atoms and protons and nuclei and electrons and things of that sort, right? So you start with, and that may even be, and that's probably an abstraction of something that's more profound that we don't know yet exactly. I mean, we know a little bit more than that, but let's start at that point. But so starting at that, then you go and turn it into materials. So you can think about, if you don't want to think about atoms individually and electrons individually, you think about materials, and we define these bulk properties like conductivity, and resistivity, which is the same thing, and other properties of the material, right? We say, okay, well, as opposed to thinking about individual atoms or individual electrons, we think about this as a continuum which has certain properties. And that's where basically you can apply the Maxwell equations to this media with different dielectric constants and different conductivities and all those things. Now, we went couple steps further, which is basically we took that and we said, okay, under certain circumstances, under certain conditions, namely when the dimensions are much smaller than the wavelengths of interest, then we reduced it to even a more strict, more special abstraction, which was this concept of nodes and meshes and branches. So we reduced it to circuits, where you could actually have elements and you could have nodes, and basically the voltage across the element was defined, well defined. You had the current that went in that came out at the same time, because effectively that abstraction was tantamount to saying that the speed of light is infinity, propagation happens instantaneously, there is no charge accumulation anywhere, things of that sort. So we created that level of abstraction. So that's the third level of abstraction, right? Now, what we kind of do today is to take, and circuit analysis in general is part of that, is taking that abstraction one level further. And taking that abstraction and taking that problem from a physical domain, really, into a mathematical problem, turning it into a pure mathematical problem that you can solve. And what we do in the nodal analysis is, which is in fact the most powerful analysis for circuits, and we'll see why, is turn that problem into a linear algebra problem. And linear algebra is a good thing because actually even in most of the math is actually the way you solve problems in the math. About 80% of the problems in math are solved by turning them into a linear, showing their equivalency to a linear algebra problem, and then solving that linear algebra problem, or showing that that linear algebra problem can be solved. So linear algebra is a very powerful tool for that reason. So we actually we're going to be using that, right? So this is the question is, how do we do this? Nodal analysis is something that's, as you will see, it's very mechanical before we talk about it. It's very systematic, very mechanical. It's well suited for computers because it also kind of like converts problem into linear algebra matrix inversion problems, which computers are very good at. So why do we learn it? Because first of all, it is something that shows us how these problems are solved with the computer. But also, more importantly, it's our last resort. We will develop an arsenal of techniques and tools and ways to think about it. But in terms of analysis, it's the most powerful tool. Not in terms of design, because there are two sides, and we'll talk about design and analysis. In terms of analysis, it's the most powerful tool. In the arsenal of your weapons against problems, this is the H-bomb. It destroys any problem. It's your aqua regis. It dissolves anything, right? I mean, just like it takes care of everything. So if you have no other recourse, you can always do nodal analysis. Now, so how does it work? Now, I generally don't do this, but in this case, actually, I'm going to give you the procedure first, and then we're going to apply it. And we can talk about why we have that procedure later on. We could also arrive at the procedure, but I think I want you to kind of like understand the procedure. So if you have n nodes, so let's say you have a network, a circuit with n nodes. So the first step, step one, is to define a reference potential. pick one of those nodes and define it as your reference potential, also known as ground. So select reference node, aka ground. So this is your reference potential. Every voltage is measured with respect to that. Now, this is a little bit different from measuring the voltages of branches, because we remember before we had these elements, like a resistor here, a resistor there, something, inductor, capacitors, things of that sort. And you say, well, what is the voltage across this resistor? Now we are not talking about that. We are talking about a voltage of different nodes with respect to one reference node, the one we call ground. From a practical standpoint, you want to pick this node to have the most commonality among the elements, to be something that's more common among a lot of different things. And we intentionally actually design things that a lot of times so that they have a node that's common to some of them, and sometimes we don't. Now, you define voltages. So step 2 is also pretty straightforward and kind of like simple. It is that define voltages V1, V2, etc., with respect to ground. Namely, these V1, V2, V3s are voltages of the nodes with respect to ground, the potential difference between any given node other than the ground and ground. Of course, if you pick ground, then that voltage will be by definition 0. The voltage of, you could call it V0 if you want. Now, the third step, which is where most of the action happens, is apply KCL, Kirchhoff current law, to node currents expressed in terms of node voltages. And I will show you what I mean by that. V1, V2, V3. And step 4, which is a mathematical calculation step, just solve the resulting linear algebra problem. So these are the steps that take that take it from whatever was left of a physical problem and turn it into a purely mathematical problem. And this happens in a lot of engineering and science and things of that sort. You take a physical thing, you abstract it away to the level that you can apply mathematical tools that can work. So, a couple of practical points before we get into the nitty-gritty. The ground has several different symbols. You're probably already familiar with them. There are many different symbols. Some of them are used for other things sometimes, but you may see this symbol as a ground. It's kind of like a downward pointing. Let me just try to make a nicer one. Downward pointing triangle. You may see just a straight line, kind of like that. You may see this. You may even see this, although some of these are in certain kinds of parts of subsets of electrical engineering are reserved for other things, like the earth and chassis and all those things. But in our analysis, all of these are equivalent. I'll probably use a lot of this or that. Yes?
Does the orientation matter? Like if I were to draw an up arrow, would it not be?
Yeah, no, it wouldn't be ground. It would not be considered ground.
Okay.
At least it would be considered, well, if I look at it, I would not assume it's a ground. At the least, it would not be good form, to say the least. But no, so it's usually pointing down. Ground. Right? Now, okay, so this is some text on a whiteboard, right? So the only way it makes sense is basically by seeing examples of it. So let's do examples. We'll go through those examples, a couple of examples, and in that process, we'll see how this is applied and how it works. So the first example, let's start with something relatively simple. So example 1. Let's say you make a triangle of resistors. And let's say you have two current sources attached across these. And let's say, I just want to make sure that I keep it consistent with my example. Let's call this resistor R1, which you can write as 1 over G1, resistor R2, which we can write as 1 over G2, and R3, which is 1 over G3. This is I1. This is I2. So these are current sources going in these directions, and these are, by the way, you should get very, very comfortable with conductances as much as resistors. I mean, if you're not already. So anytime you have a resistor, you should, if I have a R23, if I write G23, you should automatically assume it's 1 over R23. Or if you have a G35, you should assume it's 1 over R35. Because sometimes you don't want to constantly write 1 over R1, 1 over R2, or 1 over G2. And you will see, in fact, in the nodal analysis, it's easier to deal with the conductances. Because it's based on some parallel notion of stimuli than resistors. So what do we do? So step one. So this is the circuit. Let's say this is the circuit. Before I apply anything to this, first, what's the first step if I were to do nodal analysis? Define a ground, right? So which node would you define as ground? Quite frankly, from a purely algorithmic and implementation perspective, if the computer were to be doing this, it wouldn't matter. But we do it too, because not only we want to get, solve problems, but also the nodal analysis is used, the other use of nodal analysis is to derive other results, to prove, for example, other theorems. So it's more than just a means of calculating and finding answers to given circuits. It's a way of understanding the framework and proving theorems and things of that sort too. So anyway, but if you're solving a problem, I generally recommend picking the node that has the most things attached to it. Because you will get rid of the node with the longest KCL. You want to keep things as simple as possible. So again, this is not part of the algorithm. This is a rule of thumb, right? But it's basically something of that nature. So well, generally also, and among these, I think this node is a good candidate because it has like 4 things attached to it as opposed to these things that have these other nodes that have 3 attached to it. By the way, everyone I assume that remembers what the nodes are, where the nodes are. So this is a node, this is a node, this is a node. Or you could argue that this whole piece of wire is a node, but we just limit ourselves to a point. So this is the ground. So step 1, define a ground. We connect it like that. So we define this as potential 0, and then these node voltages are V1. We call them V1 and V2. So step 2 is apply KCL, Kirchhoff current law, to each node. What does Kirchhoff current law say? What does KCL say? Yes. So one answer was current in equals current out. And that's a correct answer. However, there may be another way of saying that. Some of the currents is 0, correct. To emphasize a certain aspect of that, I would usually say the algebraic sum of the currents is 0. Meaning that they could have different signs depending on how you define. So but you're right. I mean, all of you guys are right. So those are correct things. So what you do, and this is another thing to keep things consistent. This is not fundamental, but it makes your life a lot easier, is to keep the same convention. Either do, for all nodes, currents that leave the nodes or enter the nodes. We will do leaving the nodes. So we'll write all the currents leaving the nodes. So for example, we have this current, and that current. So what we are saying is that the algebraic sum of these 3 currents is 0. So let's call this I1, lowercase I1, and let's call this I2. This is the current for resistor I2. So what does KCL say in this case? Can you state what the KCL is in this case? Can anyone? Go ahead. Capital I1 plus small I1 plus lowercase I2 equals 0. Exactly. So that's the KCL at that node. Does everyone agree? Now you may say, okay, wait, what if a current is flowing this way? Doesn't matter. If the current were, one of these currents, unless all 3 of them are 0, will be flowing in a different direction, the net current. But doesn't matter. You will get a negative number. So if this current is flowing this way, you will get I1 becomes negative 2 amps. And that means that it's going in the opposite direction. There's nothing wrong. But this way you keep things constant. So now, perhaps someone else can help me, and we have to define this. So let's call this I3. to help me write the current, use the same, different color, I3. And can someone else tell me what the KCL is? Julia.
I3 minus big I2 minus little I2 equals 0.
Yes. So negative capital I2 minus negative I2 plus I3 is 0. Exactly. I just reordered what you said, but it's the same thing. OK, so fine. By the way, for a second, just let's put this to the side. So this is like, keep this here. We'll come back to it in a second. What if I hadn't done this and I had 3 nodes? So forget about this ground for a second. If I had done 3 nodes, there would be a third KCL, right? For this node. Let's, for the heck of it, write that KCL. I'm going to write it in a different color. So who's going to tell me what this third KCL is? Any volunteers? Yes. Sorry, what was your name again? Kathleen. Kathleen is going to tell us. Negative I1 negative minus small I1 minus small I3 plus I2 equals 0. So there's a third KCL, right? That's exactly right. Thank you. So this third KCL for this third node, does it tell me anything new? Does it tell us something we didn't already know? Look at the other 2 and see if you can generate the third from those 2. Can you? The 2 black ones. Do the 2 black ones produce the purple one? Right? How do you generate those? Just multiply them by minus sign and add them. So this is not an independent equation. This doesn't tell you anything beyond these 2. So if you have n nodes, you really have n minus 1 independent KCLs. That's why you can define one node as a ground, because that's not, the KCL on that node is going to do you any good. And as you can see, if you pick the node with the most, and that goes for my rule of thumb, if you pick the node with the most things connected to it, you will get rid of the longest KCL. Yes?
But you could theoretically get rid of any node. It doesn't have to be the ground.
Well, that's correct. Or another way of, so the question is, you can theoretically get rid of any nodes. That is true. Or I could rephrase it in a different way. You could define any node as a ground. Right? Correct. But you're absolutely right. So I can produce this from these 2. I can produce this, the middle one, from these 2. There are 3 sets. There are 3 equations. You pick any 2. In this example, we have chosen the ground to be here, so we picked these 2. And I think quite wisely so, because this is the longer one. But anyway, it doesn't have to be. Even if you don't make the best decision on that front, as long as you carry it through, you will get the correct result. Right? Any other questions? You understand? So that's why, if you have an n node in your circuits, you really, really need n minus 1 equations and n minus 1 volt independent voltages, and that's why you reference it, because what are the variables we are trying to solve for, really, in the nodal analysis? What are the unknowns? Voltages, right? V1 and V2. So if I define this as a reference, with my ground back there, right, I have 2 equations which should be enough to tell me what the 2 unknowns are. So the third one is independent. So I have n minus 1. So let's see. But I haven't really, this is not the KCL. This is not really step 3. Right? Because step 3 state them in terms of node current. Node voltages, right? And how do you do that? How do you relate voltages to current? So this is also a part of that. So yes, these equations are correct. These are KCLs. But I really don't want to write them this way. I want to write them in a different way. I want to write them in terms of V1 and V2s. So can you help me out in writing them in terms of V1 and V2? So I1 is I1. I1 is a stimulus, is an input to the circuit, right? A capital I1. So the first thing I need to write in terms of V1 and V2 is I1, lowercase I1. What is it in terms of V1 and V2? So go ahead. G1, V1. Yes, he said G1. Or V1 divided by R1, right? It's Ohm's law. This voltage divided by this resistance gives you this current. We're assuming linear resistances, linear everything for now. So, and a better form, shorter form of that is basically G1, V1. Correct? That's I1. Is everyone comfortable with this? This is a very simple step, but you should be comfortable because this will keep repeating many, many, many times. Okay, good. So how about I2? So somebody else tell me what I2 is in terms of V1 and V2. Okay. Yeah, go ahead, Kabi. V2 minus V1 times G2. Why V2 minus V1? Right, but if the current is defined as flowing this way, V1 minus V2 times G2. Is it clear for everyone? You have to stick with your convention. If you stick to your guns, stick with your convention, at the end of the day, you will get the correct result. If you get flustered or you change your mind somewhere in the middle, even once, you're done. You have to be resolved. Okay, equals 0. So how about the next equation? Can somebody help me with that? So negative I2 is negative I2. So the capital I2. What's the next term? What is I2? Negative I2. Who's the next volunteer? Yeah. Minus G2 V1 minus V2, right? Negative of that. And then what is the last term? Sorry, I3? G3 V2. Okay, so now it's better, right? Now this is what that step 3 means. Express them in terms of voltages, node voltages. But now the more observant of you, probably all of you, can notice that we have what? Yeah, we have 2 equations, 2 unknowns. We have a system of equations, right? What are the 2 unknowns? V1 and V2. What are the knowns? The values of the resistors, or the conductances in this case, and the stimuli, the I1 and I2. These are the inputs. These are the things that are given to you, generally. So if you're trying to solve for V, so we have to reorder this and clean it up, right? So how do we reorder this and clean this set of equations, this pair of equations? So I can write it as this in this form. I can write them all the terms that have a V1, so I can write as G1 plus G2 V1 for the first equation minus G2 V2 equals negative I1. And then I can write the other one as negative G2 V1 plus G2 plus G3 V2 equals negative I2. Right? Everyone agrees? Yes, positive. Yes, thank you. Any other observations? Questions? All right, so this looks like something very basic. This is really an algebra problem now, right? So with algebra problems, you can write them that way, but there's a more compact, more advanced way of thinking about it. Not really that much more advanced, but it's a little bit more advanced. It's just writing it in terms of matrices, right? You can write it in terms of, so instead of writing it this way, I can write it as G1 plus G2, negative G2, negative G2, G2 plus G3 times V1, V2 equals negative I1, capital I1, plus or positive I2. Right? So now you have a matrix multiplied by a vector of unknowns producing a vector of knowns. This matrix is a very important matrix. This is a very special case. This is a special case of it. We'll see how it generalizes. This is called the Y matrix, capital Y. And the reason Y is chosen, letter Y, because Y stands for admittances, is a sign for admittance when we talk about admittances, pretty short soon. And it's, in general, this will be a form of admittances. Conductances are a special case of admittances, the same way that resistors are a special case of impedances. So this is a matrix Y. This is the vector V. And this is the vector of stimuli I. So I have a matrix multiplied by, I put it like tilde on top of it to emphasize that's a matrix, and I put these arrows on top of them to emphasize that they are vectors. I mean, they're, later on, people start dropping them, but for now, I think we'll keep them there to keep things consistent and clear. Right? So really the equation we ended up is this. Y times vector v, the y matrix, times the vector v is the stimuli vector I. But this is not the solution, right? This is a problem. So how do we solve this problem? How do we solve this problem? What's the method for solving this problem? Say again? Invert y, right? And apply. So you apply the y inverse, the inverse of the matrix to both sides. On this side you get unity. On the other side you get y inverse. So v, so the solution is really applying the y inverse, the inverse matrix, times is. So this is how you find. And when you do that, you remember I told you this is like the most powerful tool? Because it first of all generates all the voltages. Even if you need 1 voltage, it generates all the voltages when you do this, right? And there's no limitation in terms of what circuits we use and all those things. So now in this case, the other thing that, so let's talk a little bit more about this. And we'll do numerical examples of this, quite a few. But just before we do that, let's talk a little bit about this. Look at this Y matrix. Can you say something? Can you make some conclusions? I mean, I know it's kind of always tricky to draw conclusions and extrapolate from one example, right? Our brains are amazing extrapolation machines. They are made to extrapolate. And the problem is that in the absence of sufficient data points, or in the absence of biased data points, I can produce examples. And this is not limited to science or engineering. This applies to social systems and all those things. I can produce any example of anything. And if that's the only example you see, I can give you 2 or 3 special examples, and I can bias you in a way that I want, to think any way I want you to think. And unless you expose yourself to various examples and understand the weights of these examples, you really can't extrapolate. But now in this case, let's try to do that. Let's try to make that mistake. So let's try to see if we can extrapolate from this. Can you look at that Y matrix and come up with a rule? Say, well, maybe I didn't even have to write this Y matrix. Could I come up with it by inspection? Could I define a rule that would have generated this Y matrix without having to go through all of these steps? And we can verify if that hypothesis is correct or not later on, but just make something up. Julia?
This isn't a rule to find it, but it looks symmetric.
Okay, so one observation is that she says it's symmetric. It's a good observation. That's fine. Good. So far it seems reasonable, I mean, based on the one example. Yes?
The diagonal from top left to bottom right would have the sums of the
Conductances?
conductances, and on the edges, you would have, depending on the signage of the ones on the diagonal, they would have a certain number of the middle term of the conductances.
So the statement is that the diagonals contain the sums of conductances, and the off-diagonal terms have some other conductances. Is that kind of sure? So that seems to be correct. Yes, that's correct. But that's not enough to write it unambiguously, right? Can you come up with a rule that at least in this case you can write it unambiguously? Kavya, and then in the back. Start this way. There, go.
So the edges will be the.
When you say the edges, I'm sorry, what do you mean by?
So like she said the ones that are not on.
Off-diagonal terms.
Will be the negative of the conductance between that the row number and the column.
Okay, so this is, the hypothesis is that the off-diagonal terms are the conductances associated, connecting those 2 nodes associated with those numbers, right? So this is node 1 and this is node 2. This is element 1, 2, and 2, 1. And it seems that it would be negative of the conductance connecting those 2 nodes. That's a plausible hypothesis. How about the diagonal terms? Any observations about what is on the diagonal terms on the 1, 1? So element 1, 1, which is associated with node 1, right? What do you see? Yes? Go ahead. And then, say,
Me?
yes, Julia, sorry.
The conductances that are connected to V1.
Conductances that are connected to that node. Anything else? The same thing, you want to say the same thing? Sorry. Yeah, so the hypothesis is that it's basically the conductances attached to that node directly. And those two rules seem to produce, at least in this example, the correct answer, right? So that is, those two rules are, in fact, correct. In fact, with some caveats. We'll talk about that. As long as, so don't read too much into those two rules, but as long as, I can tell you what the condition is, as long as you don't have dependent current sources in the network. The observation that this is symmetrical is correct, and the observation that these terms, the diagonal terms, are the conductances directly connected to that node, and the off-diagonal terms are the conductances attaching those associated nodes with the net minus sign, is a correct observation. We'll see more. But so it's good to come up with hypotheses as long as you realize these are hypotheses, right? It's fine to theorize. It's actually a good thing to theorize. So now let's go. We'll get to that in a few minutes. But now let's see. Let's do a numerical example of this thing. So let's pick some numbers. I'm going to pick some numbers for this numerical example. Let's make resistance R1 1 ohm. So I'm going to put some numbers here. So this is 1 ohm. R2, let's make it 2 ohms. R3, let's make it 3 ohms. And let's make this current 6 amps, and that one 4 amps. Okay? So we want to find what's the answer. So we have to rewrite the Y matrix. Now in numerical terms. So the Y matrix now is, so the first term is G1 plus G2, which is G1 is 1 over 1 ohm, or 1 Siemens, units of conductance is Siemens. And then R1 over R2, which is 1/2. The other term, the 2 to the diagonal term, is going to be 1/2 plus 1/3, G2 plus G3. And the off-diagonal terms are going to be negative 1/2 and negative 1/2. Right? So that's you can simplify this you can write as 3/2, negative 1/2, negative 1/2, 5/6. Okay? So the problem you're trying to solve is 3/2, negative 1/2, negative 1/2, 5/6 times V1, V2 equals. Now, by the way, we forgot to talk about something on the right-hand side of it. How do we come up with that? I'll do it in a second, but let me just write that first. It's negative I1, so it's basically negative 6 and plus 4. So this is the linear algebra problem you're trying to solve, right? It's a linear algebra. This could be anything. It doesn't have to be a circuit. It doesn't have to be even electrical. It doesn't even have to be anything physical. It's a mathematical problem. Now, by the way, I forgot to mention one thing, going back for a second here. So we talked about some sort of hypothesis or some rule we came up for defining the elements of the Y matrix. How about the right-hand side? Because we need to have this thing to have defined the problem as well, right? What are the right-hand sides associated? So for node 1, which is element 1, what is this? Yes.
It seems like the current source attached to
Yeah, you say it seems like the current source attached to it, and that's correct, but that's not sufficient. It doesn't define things uniquely. Yes?
The currents going out of the node will be negative, and the currents going into the node will be positive.
So what would I write here? Would I write the current going into the node or the out of the node to get this sign? Current going out of node 1 is I1. So it would be positive. So it has to be. So when we wrote KCLs for currents leaving the node, then because we moved it from left-hand side to the right-hand side, the rule becomes these are the currents entering the node, associated nodes. The sum of all the independent current, all the stimuli current entering that node. If you had defined it the other way around, it would be the other way around. But so if you keep that convention. So, and this is basically how you get to this. So that's fine. So we got to this linear algebra problem. And you should be able to invert matrices cold. At least you should know, at least a 2 by 2 matrix for sure, you should be able to do it cold. Right? So how do you invert matrices? What's the process for inverting a matrix? In general, if I give you a matrix, what's the inverse of a matrix? Yes?
You just like attach like you like append the identity to the side and like do operations on the entire thing. So like the left side turns into the identity and the thing on the right.
I think what it sounds like you're describing is like an algorithm for a 3 by 3 matrix, I think, in particular. But that's fine. So you need to, again, know this algorithm very specifically. That's fine. That's good. I mean, I think you have the right elements in there. But you need to be on top of this algorithm. Sometimes I joke with various people say, well, with math, you cannot be imprecise. It's not something you can argue one way or another. Yes?
Determinant times the transpose of the adjacent matrix. Identity matrix.
Cofactors matrix. Yeah.
Cofactor.
Cofactor matrix, yes. So the correct answer is, it's basically the Y inverse is the cofactor matrix transpose divided by the determinant. You can write as determinant or just as absolute value. Let's write it as determinant to emphasize it, of Y. Now, what does this mean? What does cofactor matrix mean? What is the meaning of that? So I'm going to explain this to you. Again, I know you've probably seen it. You should have seen it. But we want to make sure that we're on the same page. So here's some. What is the cofactors matrix? So let's say you have a matrix. Right? You have like whatever, y11, y12, etc., etc., y21, y22. This could be y13, etc., etc., etc. y31. So the cofactors matrix is a matrix whose individual elements, so the C11, so listen to this carefully, is the element that you get when you eliminate this row and this column from the Y matrix. So eliminate this row and this column and calculate the determinant. It's the determinant of what is left. So if it's an n by n matrix, what is left becomes n minus 1 by n minus 1 matrix, right? And the determinant of that matrix is the cofactor associated here. So these are all the cofactors. So you calculate the cofactors, and then you transpose it, meaning that if this becomes a mirror, and you flip it this way, right? Cij becomes Cji. Okay? And then you divide it, scale it by the determinant. Yes?
Doesn't the algorithm that IDEO said work for 2 by 2 matrices as well?
Correct, 2 by 2 and 3 by 3. Yeah, but I think, and you can actually extend it to higher levels too.
Like so basically like if you append the identity to like your initial matrix Y and then do like Gauss-Jordan elimination such that like you achieve an identity matrix in like your initial, like what was initially Y, like by applying those same operations to the identity you should get.
Oh yeah, you can do that. Yeah, you can always do that. Yeah, that's true. Yes, that's true. You can always do it by appending an identity matrix to it. Yeah, yeah. So that's another way of doing the same thing, essentially. Correct. Yes. Yeah. Good. Okay. So here's the thing. So this is one way to think about this. So this is basically a relative. So again, I'm talking abstract. Let's give examples. Let's start with a 2 by 2 matrix and see how this algorithm applies. And you want to understand what that means. So let's start with a 2 by 2 matrix. I don't know. Let's pick some simple matrix. I don't know. Let's do A, B, C, D. Right, in general. So matrix A, B, C, D. We are trying to invert. What do? Well, first we need to, so this is the matrix, let's say, we are inverting, Y. The cofactor matrix we have to calculate first. What is the cofactor matrix? So what is the element 1, 1 of the cofactor matrix? I eliminate row 1 and column 1. So I calculate the determinant of the matrix that's left. The determinant of a 1 by 1 matrix is its value. Right? So it's D. Now, how about element 1, 2 of the cofactor? So there's one more thing I didn't mention, I forgot to mention, is that there's a sign associated with this when we calculate the determinant, which is negative 1 m plus n to the power of m plus n. Meaning that you take that number, whatever that determinant is, you multiply it by negative 1 to the power of the row number plus the column number. So for the first one, it's 1 plus 1, row 1, column 1. This becomes 1. So how about this? What's the cofactor here? If I eliminate this row and this column and this row, I'm left with C. But it's row 1, column 2. So this sum is 3, so I get a negative sign, so I get negative C. Right? How about 2, 1? I basically eliminate this and that. I'm left with this guy. It's B, but with again, it's a 2, 1, so it's an odd. So again, I get negative B. And here, 2, 2, I eliminate this and that. I'm left with A. It's negative 1 to the power of 2 plus 2, which is 1. So this is A. So now, this is the cofactor matrix. I need to transpose it. So what is cofactor transposed? Well, I flip these upper diagonal and lower diagonals, right? So I do D, negative B, negative C over A. And then the other thing I have to do is to calculate the determinant. What is the determinant of this matrix? What is determinant of Y? AD minus BC, right? So then, therefore, Y inverse is going to be D negative B negative CA divided by AD minus BC. Right? So that's algorithm applied directly. Now, what is the determinant? What is the meaning of a determinant? Let's talk about that. Let's make a sidebar and talk about the meaning of the determinant a little bit. Because that's very important in my opinion. And again, it's a mathematical concept, but it's very important when you're dealing with them to know what they mean. So any thoughts and suggestions on what a determinant is? What does it represent?
I guess like in a physical sense, it's like the area, volume, hypervolume enclosed by like all the column vectors in like in a given matrix.
Okay.
So like if you use those vectors, if you use like all the column vectors to define like a parallelogram or like in 2 dimensions or a parallelogram,
Yeah, kind of like that. Yeah, that's right. That's actually one way to think about it. There's actually a simpler way to think about it. What you're saying is correct. There's a simpler way to think about it. It's actually what does a matrix do? A matrix really is, one way to think about it is a linear transformation. Or it takes a point, which is the tip of that vector, and moves it somewhere else, right? Or it takes a vector and moves it. It does something. It can do a change of shape. It can rotate. It can do all sorts of things. You probably have seen these matrices doing these kind of things, right? So it's a linear transformation. Now, when you perform a linear transformation, you can start with if you start with the unit cube. Now, what is a unit cube in 2 dimensions? It's a 1 by 1 square. What's a unit cube in 3 dimensions? It's a 1 by 1 by 1 cube, right? A unit cube in n dimensions is a 1 by 1 by 1 by 1 by 1 by 1 hypercube in nth dimension, right? So let's start with the 2 dimensions. Let's make it simple. And what's a unit cube in 1 dimension? It's this line with a length of 1, right? So what it does, let's say we are in 2 dimensions because we are using a whiteboard which is essentially 2-dimensional, so it makes it simple. So let's say this is the unit cube, 1, right? So I take this unit cube, so it basically is defined by these 4 points. And you perform a linear transformation, which you can represent as a matrix, a 2 by 2 matrix, A, B, C, D. And it turns essentially turns these 2 points into 4 other points. So this is a point 1, point 1, 0, point 0, 1, point 1, 1, and point 0, 0. It moves them to 4 other points in general, right? What determinant is is the ratio of the area of this new shape to this old shape, which was 1. In other words, it's the area of the new shape. But in general, if you start with something whose area is not 1, it's how much it changes the area or changes the volume of a unit cube. That's what determinant means. It's the meaning of a determinant. Okay? Now, let me show you, let's look at some examples, right? So let's just pick some examples. So my first example, basically, let's say my matrix transformation is 2, 0, 0, 1. What does it do? So let's just do color coding a little bit. So my first transformation is 2, 0, 0, 1. So what does it do? So let's see. What does it do to point 0, 0? If I put 0, 0 here, I get 0, 0, right? So 0, 0 goes to 0, 0. 0, 1, where does it go? If it's, I'm sorry, 1, 0. 1, 0, this multiplies. You remember how to multiply matrices by vectors, right? So for example, if I put 1, 0 here, you take this, multiply by that, this goes multiplied by that, right? So 2 times 1, 0 times 0, that gives me a 2. 0 times 1, 1 times 0 gives me 0. So 1, 0 goes to 2, 0. Right? Now, what happens to 0, 1? If I put 0, 1 here, I get, I get 0, 1. Because this does give me 0, and this gives me a 1. So this point stays where it is, and point 1, 1 goes to 2, 1. So I've defined a new shape, so this is 0, whose area is what? 2, right? What is the determinant of this matrix? 2, right? Let's do another one. Okay, yeah, 2 more. This is a little bit more. So let's do 2, 1, 1, 2. So let's say this is our new transformation, right? What is it going to do? What is it going to do to point 0, 0? 0, 0, right? So 0, 0 is going to stay where it is. How about point 1, 0? This point, where does it take it? It takes it to, 1, 0. It takes it to 2, 1, right? So it takes that point to here. So this guy goes there. Now, what does it do to 0, 1? One, 2. So it goes to 1, 2. Goes here. So that point goes here. And what does it do to 1, 1? Goes to what? Where does it go? Tell me. You should do this one. 3, 3, right? This gives me 2 times 1 plus 1 times 1 is 3. This gives me 1 times 1 plus 2 times 1, 3. So it goes to 3, 3. So somewhere here. So it takes that square and takes it into something like that. What's the area of this shape? Well, there are different ways to calculate it. You could form a grid. I mean, there are many different ways to calculate it. It's simple. So I'm just going to oversimplify it here. So make a grid of 9, okay, and see what is in the grid and what's outside the grid. So the grid of 9 has a total area of 9, right? What is the area? So I have these 2 squares that I have to take out. So that's minus 2, right? I have these 2 guys. What's the area of these 2 guys combined, this triangle? 1, right? Because the 1 times 2 is a triangle divided by 2, 1. So these 2 give me a 1, correct? This is basic stuff. These guys give me another 1. These guys give me another 1. And these guys give me another 1. Did I miss something? 1, 2, 3, 4, 5, 6. So I'm missing 1. 1, 2, 3, 4, 5, 6. So there should be 6 ones. Okay. So it's 9 minus. Did I get it right? No. Yeah, I've already calculated that. That's fine. Sorry. So, okay. 9 minus 1, 2, 3, 4, 5, 6. Okay? Sorry. Sorry about that. All right. So it's 3. So the area of this thing is 3. What is the determinant of this matrix? 3. Right? So that's what a determinant means. Now, let me ask you a question here, a side question, which is important, very important actually, even in what we do. What if a determinant is 0? What happens? Let's come up with a matrix that has a determinant of 0, right? I don't know, 1, 2, 2, 4. Think about what it does. What happens? From what we learn about the meaning of determinant, what happens if the determinant is 0?
Turn the square into a line.
Right, it crushes it into a line, right? Now, when you crush something into a line, remember, inverse operations are things that take this from, so if this is like, I don't know, matrix whatever, y, if I go with y inverse, I should get back my square. But if I crush something, I lose information. I don't know exactly where everything is anymore. So I may not be able to uncrush it. There's more than one thing that crushes into a line. So how do we know which one of them was the one that got crushed into the line? That's why you can't invert a matrix if the determinant is 0. Mathematically, you will see it because the determinant is in the denominator of that matrix inverse. And if it becomes 0, then it becomes undefined. But also from a more geometric perspective, what it does is that it just crushes it. And you can try, you can verify. Try it with this. And see that it does actually do that. There would be 2 points that will fall on top of each other. And then what happens is that when 2 points fall on top of each other, you can't you don't know where to take them back. All right, so let's continue quickly, and then we'll let's do a quick example, and then we'll continue our discussion. We'll take a little break, and then we'll continue our discussion. So let's go back to our example. So let's go back here where we left off. We haven't solved this problem, but now we have the tools to solve it, right? So it's pretty straightforward to solve this problem. Let me just delete this stuff. Now we want to solve this. If you want to deal with this, really, sometimes it's easier to multiply each. You can, if you have an equation like this, you have a matrix equation like this, you can multiply each line by a separate number, and nothing will change because essentially you're multiplying both sides of one of those equations by the same number. Nothing would change. In this case, actually, I will multiply the whole thing by something. I could have done it line-wise, right? Row-wise, more accurately. I multiply everything by the least common denominator, which is 6, to get rid of the fractions. So if I multiply by 6, I get what? I get 9 there. I get -3, -3, and 5 times v1, v2 equals, and this side needs to be multiplied by 6, -36, positive 24. So now I need to invert this matrix. What is its determinant? 9 times 5 is 36, minus 9. I'm sorry, 9 times 5 is 45, minus 9 is 36. So the determinant is 36, so I get 1 over 36, times, I have to form my cofactor matrices. So I get a 5, I get a 9, I get a 3, and a 3. So that's my y inverse. Now I need to multiply it by IS to get the voltages. So if I put IS here, and I want to get my voltages, I would put my voltages IS, so it's negative 36 and plus 24. So if I do it this way, I can take this 36 and multiply it by that, 1 over 36, to get rid of those, kind of scale these. So that makes my life a little bit easier. I can make it 5, 3, 3, 9, 1, and negative 1, and plus 2/3. And this should be pretty straightforward to calculate. Again, something that if you're not comfortable with, you should get comfortable with quickly. You take these two, multiply them by these two, and add them. Take these two, multiply them by these two, and add them. The way in my mind, the way I think about it, I always thought about it as this motion. Right? So 5 times minus 1 is minus 5, plus 2 is negative 3. And 3 times negative 1 is negative 3. Plus 6 is plus 3. So v1, v2 are those. In other words, v1 is negative 3, and v2 is positive 3, plus 3. So you've solved this problem. You've solved the mathematical problem now, essentially. OK? All right, let's take a quick break now. We'll do more examples when we come back, and we'll talk about more cases, more special and interesting cases.